Thanks a lot for the introduction. My name is Fengwei Zhang from Southern University of Science and Technology. And unfortunately, my student Yiming, he cannot be here today. So today I'm going to present our work, Shelter, extending ARM CCA with isolation in user space. Confidential computing is an emerging term, and basically the idea is we are trying to use the hardware-assisted trusted execution environment, such as Intel TDX and the SCV ARM CCA to protect the data. And ARM recently introduced the confidential computing architecture, and as you can see from the figure, basically it introduced two additional words. One is called ROM, okay? The other one is called root. Okay, root is not new. It's something we had before for the exception level 3. Okay, ROM is a new word. However, for the current version of CCA, it is still in the early stage, and it only construction of the ROM's virtual machines. Okay, and also it basically leverages hardware-based virtualization to do the isolation. Okay. For the motivation of our work is we are trying to cooperate with CCA hardware to provide user-level isolation, similar to, for example, Intel SGX, right? And also we want to complement to CCA's ROM VM architecture. The figure basically, what we want to show is that if you have an app, you can put it into Shelter, become a secure application, and then we can support that by using our Shelter framework. All right, so before we dig into the details, let's talk about the threat model and assumptions, okay? And in our threat model, we assume OS could be compromised, hypervisor could be compromised, secure world could be compromised, and even the ROM world could be compromised, okay? That's our threat model. And the monitor is trusted, which is exception level 3, or you call it root world in CCA, okay? And we don't consider physical attacks, set channels, denial of service, those are out of scope. Okay. And also we assume that there is a remote attestation support and secure boot. Okay, here is the design of Shelter. Okay, let's take a look at the figure. Okay, so we have something called a ASAP. That means called a shared application. Okay, as we can see in the figure, we have 4 words. Typically, we have normal word, right? That's what we want for the Android, iOS, or those kind of normal operating system. And also we have the secure word, okay? And also we have the ROM word, okay? That's what we have on top, right? And also in the bottom, in the middle, we have the root word, okay? That's the exception level 3. So in order to support the secure application, basically we add a few components. You can see that for the gray rectangles, those are the components we added into the root word, which is the exception level 3, okay? To support the ASAP. Okay, one of the key technique we use or key approach we use is something called GPC, Granular Protection Check, which is a new feature introduced after ARM CCA, after ARM 9.2. Okay, this is something built into MMU, and basically what it does is it uses a new granular protection table called GPT. Okay, it's nothing special; it's just a page table. Okay, however, let's take a look at example for the ROM. If you are in a ROM state, okay, what you can do is when you access the memory, you can access normal PAS, called a physical address space. You also can access itself, ROM. However, it cannot access secure and root PAS. Okay, so basically this is going to be enforced by the GPT. Okay, however, GPC is nice. It does not satisfy with our goal, which is we are trying to do the isolation between the ASAPs, and also we want to isolate ASAP from other privileged software, for example, ROM word, okay, or secure word. So what we do is we introduce a novel technology called a multi-GPT. Okay, what it does is for each ASAP, we prepare a GPT for it. Okay, and basically we can divide the physical memory or the PAS into different programs. And here is a figure shows you how we do it. So suppose you have a system, you have 4 cores, okay? 2 cores running the operating system, which is the normal operating system, okay? And for this 2 cores, we allocate a special GPT called host GPT for it, okay? So from the host GPT, the operating system, they can see For example, ASAP PS, normal PS. However, for the ASAP PS, it's not accessed right here, right? So for normal PS, it can access it. And also it has other PS in his mapping, right? However, we can set up the permissions. For the core 3, we can run something called ASAP, okay, your secure application. For this application, we give it a GPT for it. Say, hey, this is your GPT. And by using this GPT, we can see that this ASAP 1 can only access its own PAS, okay, as GPT-1 by using this page table. And for the other one, for example, if you have another secure application running on, for example, core 4, in this case, it also has its own GPT. Okay, by using those kind of multi-GPT, we can do the isolation. Okay, that's a high-level idea. All right, so here is the life cycle of a secure application. In the beginning, we want to create it. So for the creation, we do it in the host OS. So they will have the host GPT. When we have the secure application running during the execution, we use the secure GPT. Okay, and then we do the switch. Suppose there is an interrupt, or suppose there is a system call something. It's going to trap into the host operating system, and then we are going to switch the GPT back to the host GPT. Okay, so and then after we come back, we can do the execution, and so basically this is the whole life cycle for the GPT stability. For the GPT stability, we can see that actually it will have performance overhead. So one of the key techniques we use for something called like shadow GPT. I mean, the idea is very simple. It's just something like a call concept in the kernel, right? We do copy and write. Okay. All right. So the other thing we consider is about the TLB-based GPT attack. As we know, GPT is just a page table, right? So those page tables will be cached in the TLB as well. So when we do the switching, let's say from the shelter app to the normal operating system, we have to do the cleanup. Okay, this is one thing. The second thing is this for the TLB, they could be shared across core. So suppose you have one core running in the secure world, running for the secure app, S-app. The other core running for the host operating system, right? So in this case, if they have the GPT TLB share, there could have security problems. So probably they can break the isolation. So here what we do is we disable the shareable property of TLB, okay, across cores. Okay, there are a lot of details, and for example, how to do the memory management, how can we prevent Iago attacks, those kind of things. If you are interested, please take a look at the paper. And also, we implement we do the implementation for shelter. First of all, we implement the shelter on FVP. Okay, basically we are trying to prove the functionality to say that hey, this is feasible. And the TCP for shelter is 2K. Okay? And we also do compile shelter with CCA, which is released last year, November. So they released the IMM, which those kind of modules. CCA is about 8.2K, okay? That's compared to us, 2K. And also to do the performance, you may ask that, hey, you implement FVP, right? We know FVP is not cyclically accurate. So we cannot really precisely measure the performance. How to do it, right? So here, what we do is we use a ARM Juno R2 V8 development board, okay? And then we try to mimic all the GPT operations, okay? For example, we have some EL3 registers and try to simulate the register access for the GPT-related registers. And also, for example, if we want to do the invalidate TLBs, we just use invalidate TLB instructions for the TLB GPT invalidation. Okay, so basically we are trying to simulate what we have done for the FVP on our ARM Juno V8 board. Okay. Okay. So this is for the performance results. So here we have the dark one is the application running on Linux. Okay. For the white one is the application running on shelter. Okay? As we can see that even for the larger applications like Apache, Memory Cache, Nginx, those kind of larger applications, you can see that shelter incurs less 50% runtime overhead, okay, compared to the applications running on Linux. And as we said, we also did some optimization for the GPT construction, and we use this shadow GPT concept, and then as you can see from the experiment, we reduce 77% overhead in terms of ASAP creation. And the other thing is we do the comparison with the CCA's VM-based approach. And here we have application running on Linux, application running in Shelter, application running on Run virtual machine, and also application running on Vanilla virtual machine. Okay, as we can see that actually Shelter introduced like for these three larger applications, Apache, memory cache, Nginx, we can see that the Shelter introduced about 11% overhead, and the CCA Run virtual machine like 32% overhead. And the Shelter, in conclusion, Shelter leverages CCA hardware primitives, and basically it can create a new user level. You call it enclave, or you call it TE, or you call it, basically it's an isolated execution environment, right? And it is complementary to CCA's primary real VM style architecture, and also it has a smaller TCP compared to CCA, and also it achieves a lower performance overhead. And for us, we don't need to modify any hardware. We basically leverage the existing hardware features. Okay, and also we open source a Shelter. If you're interested, go ahead and download it and run it. Okay, so thank you very much for your attention. I will be happy to take any questions if you have.